Hi everyone, in this video we're going to see how to use the determinant of a particular matrix to determine whether or not 4 points are collinear in a plane in three-dimensional space. So to start, let's remember what the equation of a plane in three-dimensional space looks like. So we have 3 variables and their coefficients and a constant term that when we think of writing linear systems, we sometimes think of them this way with the constant on the other side of that equal sign so that we can set up an ax equals b type problem. But in this scenario, I want to think of d, that constant term, as being on the same side of the equation as all of the other terms. Now our problem is to determine whether or not some set of 4 points is coplanar in this three-dimensional space. And as we know, just like 2 points determine a line in two-dimensional space, 3 points determine a plane in three-dimensional space. So once we have one more point, that P4 here, we are asking really, is this point P4 on the same plane as the plane determined by P1, P2, and P3? So now we can rephrase this question in a more useful way that'll give us an idea about how to compute what we need to compute. So let's ask if there exist A, B, C, and D so that the coordinates of these points all satisfy that equation. So do there exist numbers A, B, C, and D, not all 0, so that the equation above that I've labeled with the star holds for all of those points? Well, if those numbers do exist, that means that we have a non-trivial solution to the following linear system. So we're going to take each one of our points Pi, so Pi is P1 through P4, and double index them so that we have an x1, x2, and x3 for each one of those. And now our linear system we can write down as the following. Okay, so let's break this down a little bit. Think about multiplying out these 2 matrices and think about what you would get, right? So if we take the first row and multiply by the only column of the second one, we're going to get A times x11 plus B times x12 plus C times x13 plus D times 1. And the right-hand side is going to tell us that that's equal to 0. That's exactly the equation of the plane, the way we've written it here. An obvious question, right? Why are all these 1s here? And it's because it's for our constant term. It's a placeholder for our constant term. When we multiply D by 1, that's ensuring that we're allowed to have this constant term D, like we have in the general equation for a plane. Okay, so let's name this matrix. I'm going to call it A. Now, we understand about how determinants can tell us something about the solutions of a linear system, right? We know that if the determinant of A is not equal to 0, then the system has a unique solution. And since it's a homogeneous system, we know automatically what that unique solution is going to be. So because this system is homogeneous, that unique solution is the 0 vector. A equals B equals C equals D equals 0. So in other words, it's only going to be the case that this equation is true for all 4 of those points if A, B, C, and D are all 0. So now what if the determinant of that matrix is 0? Well, in general, for a linear system, that means there are either no solutions or infinitely many. Now, in the case of a homogeneous system, I know there's not no solutions because the 0 vector is always a solution to a homogeneous system. So if the determinant is 0 and there's at least one solution, then there have to be infinitely many. So reviewing the observations that we've just made, if we're given 4 points and we want to know if they are coplanar, that is, do they all lie on the same plane in three-dimensional space, we're basically asking if there are coefficients that would give us the equation of a plane that would end up being valid no matter which of these 4 points we plugged in. And we rephrase that in such a way that we could actually write it down as a linear system. Are there A, B, C, D, so that all of these things, when we carry out this multiplication, we always get 0. And then we made this observation that if the determinant's not 0, then the answer is going to be no, they're not coplanar. There aren't a set of those 4 numbers A, B, C, and D not all 0, so that that equation can be true all the time. And if the determinant is 0, then there are infinitely many different solutions for A, B, C, and D, and they can't all be 0. So that tells me that there are values A, B, C, and D that I could plug in for the coefficients of that equation of a plane, so that that equation would be true for all 4 of these points. Let's see an example. So here we have a set of 4 points in three-dimensional space. We're asking if they're coplanar. So again, we're looking for A, B, C, and D, so that when I plug these values into this equation, I'll always get 0 for all 4 of those points. They'll all satisfy that equation. So let's set up the linear system. I want A times 6 plus B times 3 plus C times 3 plus D times 1 to be equal to 0. And I want 4 times A plus 2 times B plus 0 times C plus 1 times D to be equal to 0, and so on. So here's my linear system. Now I just have this question: is the determinant of that matrix equal to 0? And so we have some computations we need to do. Let me set up some space for that. Okay, I think that I'll do cofactor expansion along the 3rd column because that has 2 zeros in it. So let's see. On my checkerboard grid, I'll have plus, minus, plus. So I'll have 3 times the determinant of that. And then, let's see, 3 is a plus, so minus, plus, minus. And so that's what we need to find the determinant for that one. Now for these, I think I'll do a couple of row operations just to see if I can clear out a little bit of stuff. So that row operation that I just did, adding a row to another row, that doesn't change the determinant at all. And the same with this one. I added 2 times row 3 to row 2, and that kind of row operation doesn't affect the determinant. So now I'm definitely going to do cofactor expansion along the 2nd row of both of these matrices. And for the first one, let's see, I have to think about my checkerboard. Plus, minus, plus, minus. So I'll have minus 2 times the determinant of 4, 2, 2, 1. And now same thing here. I am going to use that 3, so I have plus, minus, from my checkerboard, so I'll have minus 3 times the determinant of 6, 3, minus 2, minus 1. So I'll have 3 times negative 2, that's negative 6, times the determinant of this little 2 by 2, which is minus 4, so that's 0, minus negative 3, or minus a negative 3 is the same as plus 3, times, let's see, negative 6 minus negative 6, so that's 0. Since the determinant of this matrix is 0, the answer to this question is yes. Now, if I had computed that determinant and I had gotten a number that was not 0, then the answer would be no, they aren't coplanar, right? Okay, so that's it. That's how we can use a determinant to tell us whether or not 4 points in three-dimensional space are coplanar.